Hey guys, hope you're all doing good and welcome to a new video. Right now, the world is undergoing an electric revolution. The demand for cheaper, smaller, and better batteries have never been so high. More and more money is being poured into the research and development of batteries. New strides are being made in battery technology, but all these developments are based upon research that has been done 4 decades ago on the third element in the periodic table, lithium. Lithium is a very light metal. It falls under the group alkali of the periodic table. It has 3 electrons and an electronic configuration 1s2 2s1. Because of the presence of only one electron in the outer shell, lithium has the least amount of ionization energy among all the elements, and it is also very reactive. So this makes material an excellent choice for anode. Apart from this, individual lithium-ion cells can achieve a very high voltage up to 4 volt as opposed to just 1.5 volts with conventional cells. This high voltage is due to the high reactivity of the metal. Specific energy and specific power of lithium-based batteries are also very high. The energy density of lithium-based batteries is about 200 watt hour per kg. This is about 2 to 4 times than conventional batteries. Lithium batteries also have a high operational range in terms of temperature. These batteries are known to work anywhere between the temperatures of minus 40 degrees Celsius and 70 degrees Celsius. The shelf life of lithium-ion batteries are also very high. Some variants of these batteries can work even after sitting idle for almost 10 years at a stretch. Right now, these are some of the reasons why you see lithium-ion based batteries being used for automotive applications a lot. When exposed to air, lithium reacts with the moisture present in the atmosphere and forms a lithium oxide and releases hydrogen. Lithium is stable when it forms an oxide with a metal. The different metals in metal oxide constitute different types of lithium-ion batteries. However, the basic working of lithium-ion batteries is similar in most cases. There are 6 types of lithium-ion chemistries. They are lithium cobalt oxide, lithium iron phosphate, lithium manganese oxide, lithium nickel cobalt, aluminum oxide, lithium nickel manganese cobalt oxide, lithium titanate oxide. All right, so we are going to be explaining one of these configurations. First up are lithium cobalt batteries. The development of these batteries started in the early 1970s and was later patented in the year 1982. These batteries were strides and leaps better than the existing nickel-cadmium batteries. Lithium cobalt batteries of the same size had a higher energy level, higher voltage output, and also lesser discharge rate than their nickel-cadmium counterparts. This combination made it a huge success. These batteries were first commercialized by Sony in the year 1991 when they used it in the Walkman music players. In this battery, lithium cobalt oxide is the anode and graphite is the cathode. The most commonly used electrolyte is LiPF6, lithium hexafluorophosphate. The main task of an electrolyte is to prevent the flow of electrons through it towards the negative terminal. When connected for charging, the lithium atoms in the metal oxide get ionized and split to form lithium ion and an electron. The electrons of the lithium atom get attracted to the positive terminal of the battery and flow through the external circuit and settle down on the graphite. Meanwhile, the lithium ions, which are positively charged due to the loss of electrons, get attracted towards the negative terminal of the battery. So they flow through the electrolyte. Here, these lithium ions react with the carbon in the graphite present, forming lithiated carbon and gets trapped in the cathode. When all the lithium ions from the anode move towards the cathode, the battery is fully charged. When the battery is connected to an external circuit, the unstable lithium in the cathode splits again to form lithium plus ions and electrons. Now the electrons again flow from the cathode to the anode through the external circuit and thus produces electricity. To further increase the conductivity of the battery, lithium cobalt oxide material is coated on an aluminum current collector and the graphite is coated onto a copper current collector. This is done to ease the flow of electrons. The lithium-based batteries have the ability to work for many years but their capacity also decreases over time. This is due to the formation of solid electrolyte interface or SEI. The big drawback of the lithium cobalt batteries is their relatively short lifespan compared to the lithium-ion chemistries and limited specific power. Cobalt is also an expensive metal, and high prices were not a selling factor for this type of battery. To counter the high price of these batteries, alternative materials were being researched for replacing cobalt. Manganese was considered, and the year 1975, battery prototypes based on manganese instead of cobalt were developed. These subsequently hit the market 2 decades later as a cheaper alternative to lithium cobalt batteries. Manganese generally appears along with iron in nature and is not as rare as cobalt. It is also widely used in the metal industry to prevent the rusting of iron. So procurement of manganese was much easier than cobalt. Because of these reasons, manganese was considered to be a much more suitable material for mass production of lithium-ion batteries. The working of a manganese lithium battery is similar to that of lithium cobalt battery, but the construction is different. Here, the cathode is made up of manganese dioxide and the anode is made up of lithium. The electrolyte is made up of a mixture of organic solvents with a polypropylene separator. The working of this type of a battery is similar to that of lithium cobalt. The difference is the material which is used in the anode and cathode. The lithium manganese batteries are most widely used in camcorders and watches because of their very slow discharge rate. The third type of lithium-ion batteries is the lithium-ion phosphate batteries. In the mid-90s, research was done to use this metal as the cathode material instead of lithium cobalt oxide. Initially, this battery was not fully accepted into the market due to its low electrical conductivity. However, this problem was overcome in the recent years by reducing the particle size and coating it with an electrically conductive material like carbon nanotubes. This battery also has a very high electrical and thermal stability. Because of these additions, these batteries have really high electrical and thermal stability. Now, as far as applications, these batteries are commonly used in propeller aircrafts. This battery is also used in the EV supercar Fisker Karma. The construction and working of this battery type is similar to the lithium cobalt. LFP is used as the cathode and the graphite is used in the anode. With electric vehicles gaining popularity in the automotive domain, batteries with very high specific energy and good lifespan are in demand. This led to the invention of the NCA batteries. This is the same battery type which is used in the Tesla Model 3 cars. The construction of NCA batteries is very simple. Lithium nickel oxide metals which occur naturally are doped with cobalt and aluminum. This is done to increase the specific energy and the safety rating of the battery. The working of NCA is similar to that of lithium cobalt batteries. Although these batteries held a healthy market share initially when they were launched, they were slowly being replaced by NMC batteries, which are much safer and less expensive. NMC stands for nickel, manganese, cobalt. It is the most popular battery chemistry used by EV manufacturers as of today. These batteries have also been around for only a decade, and the working of these batteries is very similar to the lithium cobalt batteries. The share of this type of battery is expected to expand dramatically as the sale of EV vehicles is also rising. These batteries are most commonly used in cars like Chevy Bolt and Chevy Volt cars. As you can see from the charts, the NMC batteries have a much higher specific power and power density as compared to the NCA batteries. These batteries also cost much lesser than the NCA batteries, along with a higher life cycle period. Due to these reasons, the NMC batteries have been widely used in the EV industry. The last type of batteries are the lithium titanate batteries or the LTO batteries. The structure of these batteries is similar to lithium cobalt batteries, where graphite is replaced by lithium titanate oxide in the anode. The cathode can be either lithium manganese oxide or NMC. The biggest advantage of the inclusion of lithium titanate oxide is the huge increase in the charging speed of the battery. This is due to the unique structure of the LTI crystals. Electrons can leave and enter the anode quickly, as the surface area of the anode is increased. The other advantage of these type of batteries is that solid electrolyte interface layer does not form. This increases the life cycle of the battery. The biggest downside of these batteries, however, is the cost. Lithium titanate oxide crystals are very hard to synthesize and hence their increased cost. Alright guys, with that I would like to conclude this video. I know that this was slightly a long one. Please let us know in the comment section about the format of this video. Do you guys enjoy really long videos like this or do you prefer smaller videos? Your feedback will help us make better content. Thank you so much. Bye.